In our last lecture, we discussed the differences between an electric field and a magnetic field, and we also ended our discussions by talking about the unit of magnetic field, which happens to be Tesla. But for all practical purposes, we also discussed that the gauge, which is a much smaller, more handy unit, is used for everyday applications. Today, let's discuss a little bit about the magnetic force that is felt by a current carrying conductor. So the magnetic force upon a current carrying conductor. So let's assume a conductor of some arbitrary length L and a uniform cross-sectional area A. And let's assume that there's a current I that's flowing through this particular conductor. Now, in our previous discussions, we discussed as to what would be the force felt by a single charge which is moving through a particular velocity through a magnetic field, and that was given by Q, V, B, where V and B are vectors and Q is the charge of the charge carrier that is moving through the external magnetic field with magnetic intensity given by capital B. Now, to use the same thing and apply it to an entire conductor which has current I flowing through it, let's start off with a couple of assumptions. One, we already said that it has an arbitrary length L and an area of cross section which is uniform across the conductor, which is capital A. So if this is the case, then my force, I can write it as M into L into A. What is NLA? So I am assuming M to be the density of charges per unit volume. So if I take any one particular cross-sectional area and I want to find out what is the total number of charges. So in this case, let's assume the current is being carried by the movement of electrons. So the charge carrier here becomes the electron. So in that case, I am assuming N to be the density of charges per unit volume. So what does N into L into A give me? N into L into A gives me the total number of electrons across the entire length of this conductor, because I am multiplying N, which is per unit volume, the number of electrons per unit volume, multiplied with the total length into total area. Total length into area gives me the volume of this. So volume of this entire conductor multiplied by N gives me the total number of electrons that are present, which are available for conducting the current. This into Q, because Q is, in the previous equation Q was one charge, but now this is the total number of electrons that are available for me to conduct the current. So this into Q gives me the total charge present in this conductor. So Q into, what is the velocity with which the electrons are moving? So we had discussed this in a bit of detail in the last chapter, wherein we talked about a concept called drift velocity. So on a whole, electrons exhibit drift velocity while they are moving in the presence of a potential difference or an electric field. So each electron is moving with the velocity Vd, right? That's a vector. In the presence of a magnetic field, so I'm assuming that this conductor is placed in between two big magnets, let's say two big magnets which are exhibiting a magnetic field of strength capital B. So this becomes my new equation, which represents the force being felt by this conductor. Now if I take this a little further, we were also had discussed about the concept of J. What does small j represent? If you recall, J represents current density. And it's given by the unit volume of electrons into Q into drift velocity. So J is given by N into Q into Vd. So N, Q, Vd. So I club them all together and replace them by the letter J. So my equation now becomes J, L, A into B. Now where did the drift velocity move? So to make up for that, I have now this becomes my new equation for the force being felt. Now we also know from our discussions in the previous chapter that current I is given by J into A. Current I is equal to the current density into area. So if I substitute this back in this equation, then this equation now gets modified to F is equal to I L B. But I have to compensate for Vd, because Vd was a vector, remember? It had a direction and a magnitude. Magnitude has been taken into account for, but direction has not been accounted for. Hence, I shift its direction to L. So L, I converted it to a vector, which means to say that L is a vector having a direction given along the length of the conductor. So my F becomes I into L dot B. So I is current and that's not a vector, but L and B are now taken in as vectors. So that gives me the force being felt by a current carrying conductor. So we arrived at the force that's experienced by a linear conductor. So we arrived at our equation for a linear conductor. Now suppose a conductor is a wire which is circular in shape. Then what would be the force being experienced by it? So in this case, what we do is we divide this wire into small linear pieces, each of length dl. So dl1, this another small length dl2, another small length dl3, and so on up to, let's say, the last piece, which is again linear in length, dlj. In that case, the net force that's being felt by the current carrying conductor, which is not linear in shape, will then be a summation. It will end up being a summation over all j. Over all j, we sum up the forces being felt by each of the individual linear pieces.